Let's discuss a question on machine design where we need to basically find out the diameter of the pin which is in double shear and the loads are given as shown. To get first the loads, unknown load P, well the entire structure is in equilibrium, static equilibrium. So let's first do the moment balance about A, because that would directly give you like if you want to draw a complete 3D free body diagram, you have to put the unknown reactions at AX and AY, and P is also unknown. Then the three equations sigma Fh, sigma Fy, and moment about A those three equations have to be solved in order to get the unknown reactions AX, AY, and P. We do it slightly in a different way, this problem. I mean, the other way of getting is you have to get unknown reactions AX and AY. So we do it in a different way. What you do is first you do the moment balance to get the unknown load P. So when you do that, so 5 is producing anti-clockwise moment, so minus 5 into 100 is the anti-clockwise moment about A, and P is producing clockwise, so P into 150 is equal to 0. So from this you will get to know that it's 500 by 150, which is 3.33 kilo Newton. So this is the load P. Now I mean there are two ways of doing to get the, see, ultimately we want to get the loads at A. So when you want to get the loads at A, you can either take a free body diagram and put the unknown reactions AX and AY, or okay, so there is also the load AX and AY on the pin, or looking at the figure at A, looking at the front view at A, what are the forces? 5 kilonewton is pushing it towards left, and there is 3.3 kilonewtons that is coming from the right rod, 3.3 newton. So these are the load at pin. Now if you look, this is the front view, which and the pin looks circular, but if you look at the side view, this is how the pin looks like, and it is in double shear, so it is supported here and it is supported here as well, and these loads are acting at the center. I mean both the rods, this inclined rod and the straight rods are all hinged at this point, so the loads will be acting here. So the 3.33 is like this, and 5 kilonewtons is like this, and this is a double shear, so there is a resistance here as well as here. Okay, so the net load that comes at this point, the net load R is resultant of these two because they are in perpendicular. So the net load is basically 6.009 kilonewton. Basically 6 kilonewton is the load that is acting, and it is in double shear, so both the cross section here and here will be resisting. And if let's say the cross section is A here, and this is also area of cross section is A here, so this R will be resisted by both. The stress either at here or here, the stress will be R by 2A, because, or R by 2 is the load resisted by each area. So R by 2 is the load, R by 2 is the load resisted by each area. So R by 2 by area of cross section. So this is the stress at either this and this section, which are critical. So this has to be less than your 170 MPa, which is the shear stress of the given, which is the shear stress, allowable shear stress 170 MPa. So coming back to our problem, R is 6 kilonewton and area is basically, so let me write in the Newton, so 6009.06 9.06 by 2 by pi by 4 d square should be less than or equal to 170. So directly d you will be getting in mm. D has to be greater than or equal to 4.74 mm, and we take this as 5 mm. So the answer for this, let's look at the options. So the 5 mm, so answer for this is A. So one thing is important, I mean the chance of failure in this problem is basically people forget the double shear, so that is important. And how do you calculate the load, that is also important. Thank you.